Ho. Sang Ho just recently moved to Singapore, where he's a researcher at EOS, the Earth Observation of Singapore, and he's a professor at Asian School of Environments, as well as the School of Electoral and Electronic Engineering, Nanyang Technical University. And Sang Ho is going to talk about urban flood mapping with spaceborne SAR, so with radar data, and it's going to talk about the challenges and opportunities. And with it, I'm going to stop sharing my screen and let Sang Ho try to share his screen.
Okay. Ooh. Okay. Am I sharing my screen?
Perfect. Yes. Thank you.
Okay. Thank you, Albert and Sagi, for chairing this session. I've been meaning to come join and present at the Global Flood Partnership for many years, but there were always conflicts, so I couldn't make it. And finally, I'm here virtually on Zoom. I'm very happy to be here. Thank you all for coming. I don't know where what time zone you are, but I'm in the evening mode. So I hope you will enjoy this talk and ask as many questions as you like. So this is about urban flood mapping using spaceborne SAR, synthetic aperture radar, and would like to talk a bit about challenges and opportunities. Like as Albert said, I recently moved to Singapore. Before that, I spent a little more than 13 years at NASA's Jet Propulsion Laboratory. And a lot of this work was funded by NASA's disasters program and under GFRM, Global Flood Risk Monitoring community activity. Also, I've been leading ARIA project at JPL and Caltech, it's Advanced Rapid Imaging and Analysis. And I've been collaborating with a lot of partners, and including Earth Observatory Singapore, which where I am now. But I am looking forward to continue and strengthen the existing partnership and collaboration with all these people and more. So far, with the team at JPL and EOS, we've supported more than 100 major disaster events around the world. These are color-coded with red being wildfire, volcano, eruption, and yellow being tectonic earthquakes and landslides. And blues are weather events. It's not meant to be just correlated with the frequency, but you can see more recently, there are more weather events. So we went through a lot of flooding and tropical cyclones. And I want to start with this Jakarta event, because I think this is important in terms of flood mapping opportunities. This was a flash flood on the 2nd of January 2020 in Jakarta. And this is the map. This is the optical image of Jakarta. And on the day when the flash flood occurs, in the morning, this is the MODIS sensor image mounted on Terra satellite, 10:30 a.m. local time. And in the afternoon, another MODIS sensor acquired this image. Of course, it's cloudy, no surprise, because there's a flooding event. And several hours later, in the evening time, local time, Sentinel-1 acquired this during the event image. And we compare this with before event. In fact, compared it with a number of pre-event scenes. And after, before, by comparing the two, we produce this, we call it flood proxy map. And where this light blue pixel shows the extent of flood. And this was rapidly generated and delivered to the AHA Center, ASEAN Humanitarian Assistance Center in Jakarta. And they used our map to produce, to assess number of affected people and produce this report. When we did that, we had a luxury of this crowdsourced data produced by Peta Bencana in Indonesia. They gave us this push pins, where you see push pins. Those are the locations of the reported flood within ±2 hours time window of Jakarta. Time window centered at the Sentinel-1 data acquisition. And first, we produced the one on the left, and then realized that, hey, this is not matching very well. So we adjusted our threshold to produce the one on the right and delivered it to AHA Center. So how did Peta Bencana produce this? I think this is a opportunity part. When you produce some remotely sensed data-driven flood map, you want to validate it before you release it, right? And when you do that, the ground observation is one of the best. Well, there's nothing better than ground observation. So ground observation is best. And the way that they collected this data.
PetaBencana.id is a free and open source platform for disaster management for Indonesia. This video will explain how you can share disaster information using Twitter, Facebook, Telegram, or these local applications. When you tweet at PetaBencana with these hashtags, we help you input disaster information, confirm your location, add photos, and describe the situation. Then, we put your report on the map and send you a link to share with your followers.
So, by the way, were you able to hear the sound? I hope that's what happened.
Yeah, we did hear it.
Okay, thank you. They had this robot. Whenever people tweet the flood, they had this robot automatically reach out to those people who reported flood. Because some people just say flood for some other reason, right? So this was brilliant part. They reach out to those people who reported, who said flood, and then have them confirm that that's what they meant, that this is a real flooding, and do you mean it? And instead of running algorithm, machine learning, some sophisticated automation way, they just ask people and use the data of only those who responded from those people. So that was quite successful, and perhaps one of the most effective way coming from the ground who are affected. Urban flood mapping, there are always people, right? So why not use people's contribution? So this was quite successful case. And then more recently, we produced this flood extent map of New South Wales in Australia, March this year. It's map produced by Noel Ulloa at National Central University in Taiwan. So flood proxy map from Sentinel-1. And the weather events doesn't always produce flooding. In this case, tropical cyclone caused building damage. And we also produce damage map. In this case, we call it damage proxy map. using Sentinel-1 SAR data, we produced this map that shows a color pixel from yellow to orange to red indicates increasingly more significant damage observed on the ground. I mean, observed from space, whatever happened on the ground, if it's significant change, the radar satellite can see it. And that is not just opportunistic. We developed this algorithm long time ago, like 2008, 2009. And by using a byproduct called interferometric coherence, this is the interferogram that shows the ground deformation caused by the faulting event that caused the Ridgecrest earthquake on July 4th, 2019. And when you look at this ground deformation map, there are noisy area here. And this interferometric coherence is a sort of measure of noise of this interferogram. And then we use this noise as our signal to start producing damage proxy map. So, for example, in 2017, there was a Mexico City earthquake, magnitude 7.1, that claimed about 370 people's lives, and a lot of, but very selective building damage in Mexico City. For example, this damage proxy map that we generated shows the supermarket collapse. And this color pixel corresponds to residential building half collapse. And this map was rapidly generated from Sentinel-1 SAR data that was acquired, I think 6 hours after the earthquake. And we generated this map within 24 hours of data acquisition. And more recently, there was a Beirut explosion on August 4th due to ammonium nitrate explosion in the pier port of Beirut. And we rapidly generated this damage proxy map derived from Sentinel-1 data acquired 30 minutes after the explosion. And this map here, to date, is the most accurate map and was used by many responding agencies and NGOs. And it drew a lot of media attention. BBC, Washington Post, New York Times, National Geographic, and Fox News featured our map. So damage proxy map has been matured with funding of JPL and NASA's disasters program. And there was an event, Hurricane Dorian, that hit the Bahamas in September 2019. And we produced flood proxy map as well as damage proxy map. So you can see the value correlation. There's a correlation between damage proxy map and flood proxy map. So I worked with the visualization team of Science magazine, and they featured our map on their cover, and they even named this issue, February this year's issue, as Radar Revolution. And this correlation, spatial correlation of this flood proxy map and damage proxy map is not a coincidence. And we have been seeing that spatial correlation. In fact, in our paper published last year in Scientific Data, you can see this is in Japan and flooded by the Typhoon Hagibis. And this flooded area here, if we produce flood proxy map, our flood proxy map shows the extent of flood, like here. But in the urban area, there's a complication because the brightness change in SAR image is highly dependent on the building orientation. as well as if there's a vegetation, quickly become complicated. However, interferometric coherence was showing much more sensitive response over urban areas. You can see that the buildings here, and our damage approximate was showing the significant change over the urban area. So we looked at more recent events in floods in Cox's Bazar, so a refugee camp in Bangladesh. There was a flooding in July, 2 months ago. And we first look at amplitude change in SAR image, and amplitude difference doesn't show any meaningful signal at all. You can see this is the amplitude difference or log ratio of the amplitude before and after, before and during the flood, but you don't see any significant signal. So this is perhaps one of the most extreme case, because in this refugee camp, there are a lot of shelters. They are very closely located from each other. And so in between the shelters, there aren't many open spaces that SAR sensor can see. So amplitude image is was not the best choice. So we looked at the interferometric coherence and produce sort of damage proxy map in this case, and then collected the building footprints acquired from OpenStreetMap, and those buildings, those shelters that correlates with co-located with a significant signal in our damage proxy map. The problem is, if you tweak, so this is a ubiquitous problem. When whatever method you use in remote sensing data, whatever data you use, at the end, you have to apply a threshold to make it flooded or not flooded. And when you do that, some tweak, little value tweak can make a huge difference. In this case, I think I applied 0.1 of interferometric coherence loss versus 0.3. And in this case, 2,316 shelters are affected. But if I tweak a little lower value, it becomes 20 times larger. So order of magnitude difference can easily be resulted by a small tweaking of the threshold value. This is World Food Program's reports with the list Luxembourg groups mapping. I believe they use interferometric coherence and produce 8,769 shelters affected. Probably this is reasonable number, but we don't know exactly. Somewhere it could be here or closer to here. It may be underestimation or overestimation. There are a lot of people here. It would be really nice if they could use cell phone, but sadly, the people at this refugee camp were banned from using internet and cell phone. So that's not an option. So that crowdsourcing that Peta Bencana is collecting is not available everywhere. Sometimes we just have to rely on our past experience. I bet List Group, they use their study results from the Hurricane Harvey results that they published. So there's challenges still remain. However, we're still working on improving our methods and accumulate our experiences and learn from the lessons from our real response support. Now, that I moved to Singapore, I'd like to introduce new members of this EOS, Earth Observatory Singapore Remote Sensing Lab. This is me, and this is Cheryl, my new PhD student, and this is Lynn, new mission controller, and this is Shitong. She is the head of DevOps. So we're a small group, but highly efficient, and we will continue doing innovation for better response support. Thank you, and I'd be happy to take your questions, if any.
Thank you so much, Chang-Ho. That was wonderful.
So we have some questions in the, or at least one question in the chat right now. I'll read it out loud. That's from Arjan. Okay, great presentation. I was wondering if the Indonesia Jakarta case, did you get any feedback on the map you produced? Let's start with this one. There's several questions here.
No, we have not. It turns out it's one of the most difficult part of this response cycle. So when we provided this map, the report was produced. That was part of that was sort of a feedback. But what we need and more useful feedback would be, hey, that was an overestimation. Hey, that was underestimation. Or this part was overestimated, but that part was not. That kind of detail, spatial detailed information is super useful. In fact, there was Cyclone Harold that affected Vanuatu and Fiji, and we worked with the World Food Program. And right after that, because everybody's busy and there's no good time. You have to make yourself available. Right after that, we dropped everything and World Food Program, and we had a meeting to talk about the response effort, what went well, what went not so well, and we learned a lot. One of them was how they produce number of people affected. After we learned that, the next event was Cyclone Amphan that hit India and Bangladesh, and we used their approach to produce higher level products upfront rather than just delivering the raster image. So that was quite successful. But yeah, that's a great question. Collecting feedback is not always easy, but it's critically important.
So Erjan have more questions and comments, but I want to give opportunities to other people. So please go back after your talk and respond to him. And okay, I'll go to the next question from Cohen. You mentioned that you tailored the map with the local feedback. Was the tailoring just the threshold?
Yes. There are filtering to remove like isolated small pixels because we know water, flooded water bodies are they tend to show up together because the topography, smooth topography. There are many different ways to handle it. One of the ways we do is simple filtering. Another way we're also applying is the spatial temporal machine learning, like LSTM, convolutional LSTM type, or paired RNN. When you do spatial temporal convolutional LSTM, you encourage water flood pixels to get together. Yet another way is to use certain algorithm like the region growth. So once you know this pixel is a flood pixel, then you let it grow until it hit the boundary. So there are several ways to handle, but yes, we do apply those steps, and then at the end, thresholding. And then when we apply threshold, we look at independent observation. Sometimes optical imagery, sometimes crowdsourcing, sometimes just media report, a few points, but it's still way better than nothing.